Hello, everybody. Good afternoon. Thank you for coming to the Geotalk. And today I would like to welcome the speaker, that's Frikkie de Beer. And he started his career in 1888 at the former atomic 1988. I saw many eight. He was at the former Atomic Energy Corporation, now NEXA, in the field of non-destructive investigation of nuclear materials. And today, Frikkie is heading the radiography tomography scientific group and has established the only neutron tomography capability in South Africa in 2003. And now there is a complementary micro-focus X-ray tomography since 2011. These instruments are utilized in multidisciplinary research projects by researchers and postgraduates and are contributing to the National System of Innovation in South Africa. His current research is focused on the application of neutron and X-ray radiography and tomography in hydrogen fuel cell technology, porous media characterization, and the establishment of a fossil preparation laboratory to support the paleoscientific community in the 3D computed tomography scanning services at NEXA. And I say thank you, and the talk of today is neutron and X-ray computed tomography as analytical probes applied in the geosciences.
Thank you very much for the introduction. Thank you for hosting me as well today. I'm actually standing in for one of my colleagues who is actually just finalizing his PhD and the review marks on that. So Lunga couldn't be here, so hopefully that my visit here today is fruitful, as well as for some of the students that might be here today, that you probably will be inspired as well through the talk, and that's why I also tailor it in that way. It seems that I became now a regular at Wits University with some talks, because the last talk of mine was with the engineering faculty in 2004. So, yeah, it's quite a while. Where the topic of the talk was helicopters can't fly without neutrons, and that was quite a nice talk with neutron tomography as the key investigation probe into aspects of non-destructive testing on helicopter components. But nevertheless, it's not what I like to talk today. For the students, you have to have always a dream, and you have to take that dream to the ultimate, so not to become poor. Dream and live your dream. So I will end with also such a kind of remark from somebody else in terms of you have to dream and what you have to do with your dreams. A little bit of background first. When we talk about neutrons and X-rays and nuclear per se, we have the normal public have the perspective of electricity. So man-made radiation. Talk about electricity, talk about Kuberg, power electricity. So this is the normal way people think about, but also in terms of medical, certainly when you have a diagnostic X-ray due to an accident or something like that, we all know that route. Also in terms of the CAT scanner. But the other aspect of medical is the medical isotopes. That is all sometimes in the news, and hopefully not one of us here today have that experience to be injected with a medical isotope, etc. So, but the main problem is that the work that we are doing in terms of beam lines of radiation, X-rays, neutrons, gamma rays, are not on the forefront. But that is a kind of a hidden, something which is hidden, which should be exploited. And I think today will also be a day where you can actually learn more about what one can do with not only X-rays, which is we are all familiar with, but also with neutrons. So my presentation outline will be like that in terms of the background. For you that don't know about neutrons, a little bit more about that, how neutrons and X-rays complement each other, etc. And then I like to end up with case studies because it's quite the important aspect. But I'm not a expert in geosciences. All that I can recall here are those work that has been done at DEXA, which we supported as instrument scientists, so that we can optimize the scans, optimize the radiographs in terms of the quality and the signal to noise ratios, etc. So let us go and start off. Normally, the problem when you worked in the past was quite a destructive problem, because your samples, if you like to investigate your samples, was being destroyed in order to regain knowledge within. But effectively, radiation came to the rescue, because with light as radiation, the microscope, you can actually see much more better, deeper, or smaller spatial resolution. But the problem is this, it's a surface technique. What is hidden inside? Then radiation came to the rescue again in 2D radiation with X-rays, which we all know. But when you apply that to a drill core, for instance, you end up with the same problem. You see some changes in grayscales, but it doesn't mean anything to you. So the problem persists. So what happens is there's a rescuer, namely Alan Cormack. Alan Cormack, a South African physicist, that invented the CAT scanner that we can see, have at all universities, or most of the hospitals have the CAT scanner. But did the CAT scanner eventually, which is located at hospitals, gave us the needed information? Actually not, because those CAT scanners are merely available for human and patients. As well as the resolution in order of half a millimeter is not enough if your object of investigation is 50 micron. So effectively, even though also it's fixed with a certain potential kilovolt energy, effectively you are stuck again. So what happened is in South Africa that neutron and X-ray research instruments came into play not only at NEXA but also in South Africa to support then research, and those research areas where we can now utilize not only X-rays but neutrons in all areas, and I will focus on those as well, all areas of sciences at the end of the day. So to look at the X-rays first, let us start with X-rays and see what happened with X-rays all during the past 100 years, more than 100 years. So when X-rays were discovered, or Röntgen rays, we all know this kind of picture with the ring of his wife's hand. So in 1901, during the Boer War, those instruments already were applied on the British side as well as on the Boer side, but they were robust. You can actually see there is a bullet in between the toes. And actually what happens is the people, or the operators, were so concerned about the electricity, because there were wires all over the world, that they weren't concerned about the radiation. So a British researcher that came to South Africa lost both his hands due to overexposure of those X-rays. But nevertheless, it came into South Africa. Then in the CT, in 72, the CAT scanner, which I talked about Alan Cormack, he invented the CAT scanner with the first head scan of the brain in 1972 or 79 at the end of the day, when you received his Nobel Prize. In 2005 at NEXA, I introduced a probe where the neutrons came through, to start with 1 millimeter focal spot X-ray radiography and tomography. But then in 2011, due to due to the demand from researchers, 3 machines, 3 X-ray, microfocus X-ray machines came into play for the research community to use. One at Nexa, the one that we are running at Nexa, the one at the University of Stellenbosch, and the one here at Wits University. And the NRF supported this kind of research. So we have at this point in time another 4th machine that is at the UNISA. It's being utilized also by the Mintec. It's been run by Mintec Des Chetty in person. So these machines are now being utilized in all areas of application. What about neutron CT and what these instrumentation? So when you look at CT instrumentation, we're all familiar with the hospital CT machine. The sample is stationary. I talked about the 0.5 millimeter resolution that is not adequate for geoscientists to exploit, and it's dedicated to human scanning. When we go to a laboratory scale X-ray machine, you have a radiation source, the spot size of up to from 600 nanometer up to 1 millimeter, even 3.3 millimeter when you need more X-ray flux. The sample is on a rotary table, and then you have your detector on that side. So when you rotate the sample, you rotate and gather 2D radiographs, more than 1,000, even 3,000, to eventually improve your resolution, etc. These scans, due to the X-ray flux that is not very high, in order of 10 to the 8 photons per square centimeter per second, can last from half an hour to 3 hours, depending on also your dynamic range that you like to achieve with your detector. So the resolution you achieve then from these machines is a direct function of the spot size of where the X-rays is being generated from. Through geometric enlargement, you end up eventually if you have a smaller sample, project it on the larger detector, and that larger detector pixel size is 200 micrometers on an array of up to 2048 by 2048 pixel arrays. So this kind of machine is now located at Nexa, and some of you in the audience already utilized this machine. These machines, these kind of machines that I shown you here, are actually available overseas at most of the universities. Most of museums have these kind of machines available for their research. But also, I should not neglect then the synchrotrons facilities that are in place. There are about 44 of those facilities all over the world. They call it synchrotron light source. Because you end up here on these machines with a photon flux of 10 to the 20 photons per square centimeter per second, that when we perform one scan of half an hour, that can be done in 1 minute at those machines. But also they have improved resolution, especially the European spallation source in France, where South Africa has a collaboration where researchers can go to that machine, apply for beam time, and utilize those. But the problem is that those machines are overbooked, 5 times overbooked. And if you can't show that the micro CT that you have done at your facility at home couldn't give you the answer, then you have a good motivation to apply for beam time and to get beam time at these kind of facilities. So, excuse me, researchers from South Africa can go to ESRF, apply for beam time, and all costs is being paid by the South African government in this regard. What can you do at synchrotron light source? Chemistry, material science, magnetism, life sciences, industry. So actually it's a huge, vast area of scientific fields one can exploit. But if you can do that at synchrotron, certainly you can do that also at micro CT laboratory scale facilities. Let us go to neutrons. Neutrons, most of you are not familiar with neutrons. With neutrons, you have an aperture of 10 to 30 millimeters size. Remember, micro CT, you have an aperture of 600 nanometers to 1 millimeter size. That is because the neutron flux that you have when you rotate your sample is much lower, up to 10 to the 6 photons per square centimeter second. And then a scan can last up to 16 hours in order to achieve highest spatial resolution and dynamic range also of your sample. So the resolution is a function here of the scintillator screen. Scintillator screen is a screen that changes the photons energy into normal light photons that can be detected by a CCD charge-coupled device. And the resolution there is limited to 100 micrometers, although with a newer CMOS detector systems, the resolution can go down to 11 microns or even 5 micron with systems available at the Porosity Institute in Switzerland, as well as at the FRM2 München facility at the Technical University of München. So how does it work? You have your how does the scintillator screen system work? Your sample, where you have your neutron beam, and the mirror reflects the visible light onto a lens, through a lens to a CCD camera system, and that camera system should be outside the neutron beam because it's quite sensitive. Neutrons can actually damage your camera systems. So this is the kind of system, and the infrastructure for that you will find at a kind of a research reactor where fission is taking place, where the atom is being split and excessive neutrons can be channeled through beam lines, so that you then have these beam lines and a beam of neutrons guiding through onto your target. So this is the old neutron radiography facility at the reactor, at the Safari reactor. There is the reactor there, okay, and some highlights. In 1997, we changed from film to electronic detection in 2D. In 2003, the neutron 3D tomography, the very first neutron tomogram in the southern hemisphere, was made of a helicopter. That's why you have helicopters can't fly without neutrons. I presented this result as well because the helicopter should, the engine should be lubricated through that small hole there. And that pipe got blocked, and only neutrons could actually penetrate through tungsten in order to see the blockages in that area. The other highlight is actually the hosting of the World Conference on Neutron Radiography in 2010 at KwaMoritane here in South Africa. Okay, so our new neutron radiography facility looks like that. The old radiography facility actually is located only in that area here. So we put up about 600 tons of shielding material because you need to stop neutrons, and you can't stop neutrons with lead. So therefore, it's a kind of another ballpark to work with neutrons at the end of the day. So neutron radiography and tomography facilities all over the world is being spread in that case. So in 2010, we had a user program. We stopped our work in 2013 for the upgrade, but our new facility is being based on the reactor FRM2 in Garching in München in Germany. The reactor, there's the old reactor, there's a new reactor, and the neutron radiography facility layout is quite similar than what we foresee in our new facility in 2 years' time. Hopefully it will be operational. What about the data processing? The data processing, the flow of data when you do CT work is, first of all, you need to scan the sample. And normal scanners, hospital scanners, the head of the sample is stationary, while the detector and the source is rotating around the head. In our case, the sample will rotate, and you have to rotate the sample in many projections. We call each radiograph a projection. So you gather at the end of the day at 8 to 10 gigabyte of data. In this case, just for the raw data. Okay, so the next part of the data processing is the reconstruction process, and in the reconstruction process you have to go from 2D to 3D, and that is that reconstruction process which Cormac actually started and put into practice. You end up with a 3D virtual volume at the end of the day. So for this process of reconstruction and this 3D volume, you end up to 10 to 30 gigabyte of data. That doesn't depend on the size of the sample. If you scan a cell phone, that cell phone generates that data. If you scan the point of a ballpoint pen, that data is still being generated, but with higher spatial resolution at the end of the day. Okay, so what is this 3D reconstruction process consist of? This is the Beer-Lambert law that is we are all familiar with the intensity of our X-rays in the input and also the output defined like that. So each element, a volume in your sample, has a certain attenuation of your radiation. Okay, and in a sample there are many of those which you can then relate to add up the many of attenuation coefficients of those minerals or elements within in a single array. So the radiation is being attenuated by the material because each of these elements have a certain attenuation coefficient. So at the end of the day, you have an array sum of attenuation coefficients which you have to add in one direction. So when you switch to 90 degrees, all those in one line will be now in different lines. So that is what you end up with, a line integral, because you know the incoming and you know the incoming and the outcoming radiation value, and so you can actually distinguish then between all these elements in 3D. So the 2D projections with pixels. Through this reconstruction process, you end up with a voxel, and you have an array of voxels, which is a virtual volume of your sample. Okay, and especially Cormack have this reconstruction process that won him the Nobel Prize for Medicine in 1979. So we have now this flow of data. Now what about the 3D visualization? You have this voxel value of these voxel arrays of voxels, a cube of voxels with you. Now you can actually slice in and out any direction through that sample. You can minimize some voxels with a certain grayscale. You can maximize them. So effectively you are in control of your sample totally, and that is in a non-destructive way. Okay, so why X-rays and why neutrons? And will you get a different picture if you use X-rays and if you use neutrons? So in short, X-rays they are interacting with the electron cloud around the nucleus. So through absorption or scattering from the electrons around the nucleus, you end up with an attenuation of the materials with more electrons around the nucleus and a larger atomic number. Certainly your attenuation, the absorption and scattering is higher than with less electrons. When you look at neutrons, neutrons is a neutral particle. It flies through the electron cloud, interacts only with the nucleus through absorption or through scattering, and it's random. There is no pattern. It's not linear related to the atomic number or the number of electrons around the nucleus. So what we can see here is that we have the light elements, the boron, the hydrogen, the lithium, to be the light elements that's being attenuated, that's being scattered or by the neutrons in a higher manner than the X-rays. So the signal of hydrogen and boron and lithium, you can detect those minerals or those elements much more better using neutrons than X-rays. What about the metals and as well as the heavy metal elements? Here we see that the penetration by using neutrons is much more better than through those elements than using X-rays. The X-rays, if you look at lead, even X-rays can't penetrate through lead, but with neutrons, lead is very low on the mass attenuation coefficient scale, so you can penetrate lead very easily. So you can't stop neutrons using lead. You stop neutrons using gadolinium, cadmium, lithium, and hydrogen and boron. There you stop thermal neutrons. although you can't stop thermal neutrons or fast neutrons with these elements, only scatter them and absorb them by boron at the end of the day. So, do you get a different picture? Yes, you get when you use X-rays and neutrons on the same sample, and this is out of the Jews scientific field effectively, but it's good demonstration what you get when you use X-rays and neutrons on a cigarette lighter. And you can see here that the spiral that is a high, it's, say, for instance, say copper, or it might be steel, that spiral can be easily seen, but penetration through that is very easy with neutrons. But the pipe is hydrogen rich. That can be, the rubber can be easily seen, as well as the liquid, the fuel. The neutrons see the fuel, the X-rays can't. In the battery compartment, you hide a gemstone. The neutrons see the gemstone, the X-rays, very difficult to see that. And other elements here on the X-ray and the difference between them. So they are complementary to each other at the end of the day. So it's beneficial if you have in your country a X-ray source, but also a neutron source, in order to distinguish. And in the geoscience areas, which I'm going to showcase later, you will see that very easily. So, yeah, all boils down to resolution. What can we achieve? And if my object is in a certain resolution, will I be able to detect my object? The microfocus X-ray tomography is in the order of about 5 micron, while nanofocus is also currently popular to go back to plus about 600 nanometers resolution. But effectively, your sample is very small when you look at nanofocus X-ray tomography. What about neutrons? I told you about 5 micrometer and larger is the best. Synchrotron tomography, more than 1 nanometer is possible. There you end up with the SEM, the TEM is on that side. So this is actually what we can achieve, and we as in South Africa currently look into the micron world. We are not yet into the nano world. Although there's one machine at the University of Stellenbosch, they have a nano focus facility at Stellenbosch, to be utilized also by researchers. Okay, so let us go now to what can we achieve? What can we do? What can, utilizing tomography, and actually you can see there are many fields of application. I presented in 2004, the one on engineering on the helicopters, okay, but in biosciences, cultural heritage, there are numerous applications where research fields can benefit and do benefit from the utilization of penetrating radiation, X-rays, and neutrons. So let us look then at in the geology field.
Excuse me,
yes.
Continue. I have a question about the, I guess the analytical or the operational side and the theoretical side about focusing. I know more about X-rays than neutrons, and I know that you cannot focus X-rays. You can collimate them.
Yep.
So how can you get resolution of 1 nanometer or even 1 micron? And what I'm uncertain about is you have a sample. Let's say it's a drill core or a
yeah.
You shoot X-rays at that thing. How do you focus the X-rays on a plane inside of a 3D object, even if you rotate it?
Yeah.
So where are the X-rays being focused that produce your detectable signal? Is it detecting the entire three-dimensional object? In which case, if that's true, then how do you get that small resolution?
The small resolution, you call it an area of interest scan. So you rotate the sample at that specific point, because currently, if you have a larger sample, for instance, this is your sample, and you like to focus on one area, because in the past, the software allows us only if this whole object, if you like to focus this whole object must be in the focus area all the time during the rotation. But nowadays, the software allows us to put the sample in terms of X-rays closer to the source, so that the rotation, the area of rotation is exact at that point where you like to focus and look at in more detail, in more higher resolution. So that point is rotating exactly, although there are some information in certain degrees around the sample, which then the software ignores at the end of the day. So then you focus exactly on a small spot.
How do you focus the X-rays in a three-dimensional object, say, right in the middle of it?
Okay. You don't focus it. You just pass it through.
You
that
pass it through,
yeah.
So
the little object
the
passes
X-ray
through.
that is detected
Yes.
is seeing the integrated signal from the entire, it will be a two-dimensional line, and then at the end of the day, how do you focus it into one plane?
Okay, what happens is it's a cone beam. I can actually go back. It's a cone beam which is being detected by the detector on a 2D X and a Y scale. So when you actually have in your sample right to the source, that area, only that area that you are interested in, is being projected on the screen.
Yeah, but if that wasn't a piece of paper, it was a rock that has three dimensions.
Even a rock.
It's going through the entire rock.
Yes, that's right.
And it's not focusing on individual places.
Yeah. But the rotation, which you then project on the detector, that area is only focusing, that area is only displayed on the detector. That small area, not the whole sample, it's only that area. So that is where the geometric enlargement comes in at the end.
It doesn't make a great deal of sense to me.
Okay.
Talk to you later.
Okay, we can talk later. Thank you. All right, so let us, at this point, all the work that I'm going to display right now is a function also of my colleagues, Kobus Hofman, Lunga Baum, and Robert Nshinimara, who supported us as instrument scientists over the years to really, when researchers come to Nexa with their objects, that these guys are really expert instrument scientists, that they can produce then the best optimal radiograph and tomogram volume which you want. So these guys, I really like to say thank you very much, also in this audience, for their efforts and their dedication. Even also that all of us are also focusing on certain research areas, which we are all focusing on. And again, Lunga, I stand in for Lunga at this point in time. So he's busy with his PhD and on iron ore in the geosciences, and it will be done by the middle of this year. Okay, so let us look at the geoscience and the applications. So we have various areas, so I'm not going to focus on coal because of the time, as well as fluid flow, but the applications of utilizing penetrating radiation in those areas are vast as well. So let us start with oil and gas. When you look at hydrocarbons, again, hydrogen neutrons can see hydrogen. So on the neutron tomogram, in an oil sample filled with oil, you will see then the oil signal will be detected. While with X-rays, some high density zones can only be detected while it's transparent. The oil is transparent with the X-rays. So complementary again, the two techniques to utilize them in succession. Tar in sandstone. How much tar is available? Again, the hydrogen signal, because of the NCT, is neutron CT. The hydrogen signal shows then effectively your bitumen in 3D. Here we have a residual oil in a sandstone sample, where the green empty pores one can quantify. So with 3D, you can quantify the whole volume, about 7% of empty pores, while oil-filled pores. Residual oil that is still available within that core, which can be subtracted still. These are really available and also can be detected and quantified at the end of the day. In shale, porosity in shale is very important. So we will look at your shale an area here in terms of a smaller area, as well as your voids, which then is being enlarged in this area, because porosity in shale is very important for that economy. What about gold? Here we look at, especially here must I say that once you do X-ray and neutron tomography, the signal that you get doesn't show that this is gold, this is pyrite, this is hydrogen, whatever. So one has to benchmark your signal, your neutron or X-ray CT signal with another technique, either SEM work, either X-ray diffraction or QEM scan work. So here you can actually see how a slice through a X-ray CT represent also then a QEM scan map of gold in this regard. So actually nicely. So once you benchmark it with respect to another system, then on a certain level, because this is a slice, then you can extend it into the total volume of that sample to get them volumetric detail. Here you can see the gold, and this is work from Glenn Nwala, who did his MSc at Nexa, who is currently employed here by Nexa, or by Wits, where you have your sample, but then in 3D you have your pyrite together with your gold, and then you can, with your voxel change of, or the minimizing of the voxels for the pyrite, you end up with your gold particles in that sample, and also then a volumetric determination of the size distribution of that particles within your particle size distribution of the gold in 3D. Okay, so what about minerals? Let us go to minerals. Minerals, are there a couple of challenges? Okay, there's a beam hardening effect, especially when you have high density materials within. That also some of the software is really sorting that out. The software allows also for beam hardening effects to minimize that. These are being generated when the softer X-rays are being captured by the material in some areas, but on the edges, sometimes those softer X-rays are penetrating through. So effectively, it seems that the edges of their sample has a more brighter or higher attenuation of the beam, so that you can account for. So in this case, we have a QEM scan with one surface, and then this is an XCT where the Peritonitis mineral is actually being seen very nicely here, and this kind of yellowish. But also, when you look a little bit further on the screen here, you can actually see there as well. Your plagioclase is also visible. So there are a couple of phases with XCT, which one can distinguish due to the fact that you have different densities of these minerals. But some of them are quite difficult. And then it lends to different X-ray CT techniques that one can apply. For instance, here, when you look at porosity measurements, this porosity of two different minerals, because you have now a 3D volume, virtual volume, and each slice, these are each of the slices, can produce a certain porosity of in your sample, while when you look at only a thin sectioning of your sample, will produce, for instance, in this case, a slice 600, will produce only a 5% porosity in that sample, while the other porosities are neglected. So in this case, this porosity is in order of 3%, although the average porosity might be 1.5% in this sample. So that is where you have added information, added knowledge about your sample by having it being scanned in 3D. So when you compare then 2D and 3D results, your 3D results should be then more accurate than your 2D results in all the cases. And effectively also larger due to the fact that you have the whole volume being evaluated in terms of porosity. In terms of charcoal pyrite, and here I actually now present some of the work of Lunga Bam, which he has done over the couple of years. Each of the minerals, like charcoal pyrite or pyrite, has a certain attenuation at a certain X-ray energy. Now, to distinguish between charcoal pyrite, that is that line that is going there, and well as pyrite, that is the line here. Let us enlarge just that part. At all the energies, like for instance 70 kV and 130 kV, those two lines meeting, they have the same attenuation, but there's a slight differentiation between the charcoal pyrite and the pyrite in this area here. So by utilizing the dual energy method, by scanning at 70 keV, but as well as at 130 keV, and subtract the two from each other, the charcoal pyrite can be distinguished. But then you need to have also a kind of a standard sample that is charcoal pyrite to quantify or calibrate your data and the signal, the gray scales of your voxels respectively. So one can then, when samples have this the similar densities, utilize different X-ray CT techniques like dual energy to distinguish some of those minerals. Uraninite, exactly the same. Uraninite, you have here all these white areas here are all uraninite, but then also again size distribution of uranium particles is then possible throughout the whole of your sample. A little bit of theoretical simulations of different mineral compositions. And here I would like to highlight a couple of them. Quartz, when you have thermal neutrons and when you have X-rays. You can actually see thermal neutrons are passing through quartz very easily. So therefore you can actually have a larger samples of quartz and penetrate through that very easily with neutrons rather than with X-rays. Then you have the autopyroxenes. The pyroxenes are in this area. So you can actually see the attenuation coefficient for X-rays is quite high with respect to the neutrons. But also when you consider the two with quartz and autopyroxene, you will not be able to penetrate quartz and then distinguish this because the X-ray radiation will be attenuated by the quartz before you reach the signal for your autopyroxene. So that is the first thing. The second thing is, when you look at the plagioclase feldspar, you have again the similar situation. Much more better penetration using neutrons rather than X-rays. And then your autopyroxenes and clinopyroxenes here have a different, probably the different, same density, but different neutron attenuation coefficients. A very slight difference, while it's quite high. So when you like to penetrate through 0.83 attenuation coefficient of feldspar, you will not have a signal left to see the pyroxenes with these high attenuation coefficients. Effectively, when you have a larger, thicker sample. So theoretically, if you look at these pyroxenes with neutrons, and that's where the neutron CT has its advantage, that the X-ray attenuation of plagioclase matrix is high. The neutron through the plagioclase is low, so we can penetrate better with neutrons. And the pyroxenes has a higher attenuation than the plagioclase matrix. So this kind of sample then can be then scanned, and effectively then the CT supports this kind of applications within. So what can we find? As we could see, theoretically the X-rays can't penetrate through with the draw core. The neutrons can. So what can we expect at the end of the day utilizing thermal neutrons? Different kinds of samples with pyroxenites groups. Here we have a little bit larger. From the outside you can actually just see those, and when you make a cross section, it's been colored red, and you can actually see how it differs from small fragments. So it's very nice to have these capability, and that you can actually have throughout the sample. But also here you can see how rugged this top part is, with a boroplaque sliced in various areas, okay? And the feldspar is transparent, so you make it transparent, you only see then those pyroxenites there. Okay, so when you have this draw core, what is the process to do thin sectioning at the end of the day? Is to make a scan, make a neutron scan, because the X-rays can't penetrate through the thick sample. Then neutrons can discriminate between the clinopyroxenes and the autopyroxenes, because I think the clinopyroxenes has only a calcium atom added to its matrix, and therefore the neutrons, although these two minerals has the same density, the neutrons can separate and distinguish between those two minerals. Another drill core, okay, when you slice through that drill core, at a certain point, you only get a signal of your pyroxenes in that area. Okay, the red signal there. But this is the 3D neutron tomogram, and when you slice through it and you minimize then the feldspar matrix, you can actually nicely see how that matrix is being now minimized, and the pyroxenes actually is being viewed. So if you then make a slice prior to in that area, you will not find any pyroxenes minerals, because you are missing the like the ore kind of there. So, okay, so when you look at porosity, you can also have the permeability of that mineral. So the ultimate is actually with a certain particle size. When you determine your porosity, that you can actually create this kind of a graph where your porosity is interlinked with the permeability within your sample. Okay, so the last part is I have to look at also fossil materials, because in essence these are also geoscientific related. So the main thing is why we use neutrons and X-rays is and why neutrons is more effective in determining or looking at or finding fossil materials, because of those finding of those materials. The fossil has now has hydroxyapatite with a hydrogen within that matrix. So when it's got fossilized within the breccia material, and this is a slice of neutrons and a slice of X-rays of exactly the same sample, you can actually nicely see the signal from the neutron scan is much more better than the signal from the X-ray scan. And this allows us, because of the penetration capability of neutrons through thick material and dense material, that allows us then to get the signal of, for instance, in this case, a baboon mandible, and then researchers can actually doing some research on the teeth of this mandible without taking this sample or the mandible out of its home, which was probably a couple of million of years. Let us summarize. Micro CT probes is available in South Africa. Okay, Wits, the University of Stellenbosch, at Nexa, as well as now at UNISA or Mintec, with additional neutron capability at Nexa and also nano capability at Stellenbosch. Is becoming more important nowadays in the geosciences, because probably when you go to these kind of conferences, you will find always some CT work being presented at those international conferences. The main thing is non-destructive. You can subject your sample again to other techniques, analytical techniques as well. Neutron CT and X-ray CT can be used together to identify rocks. Addition of thin sectioning, it identifies shape and size of minerals, find hidden fractures, etc. You can quantify in terms of volume, size distribution, mineral types as well, benchmarking as I mentioned, density profiling when you use X-rays, and then also porosity measurements, pore size distributions. CT capabilities are still underutilized in South Africa. I think with the number of users at our facilities, ore studies, rocks, volcanic, fossils, all these, there are huge areas which can be exploited still. And we have an ImageRad series, Imaging with Radiation conference series. In September 2019, it will be hosted at Nexa. It is the fourth in the series, a biannual conference. I will get to the advertisement of that. But in summary, at the end of the day, when you look at neutrons and X-ray sciences, you can actually see many areas of living that is being supported by utilizing neutron and X-ray beams, with the earth sciences very well defined as one of the key areas of applications, utilizing not only radiography, where where the neutron or X-rays as a particle is interacting with materials, but also with neutron diffraction, where the neutron and an X-ray as a wave is being interacting with materials. So in this case, since utilizing neutron and X-ray beams can actually exploit all the areas of sciences currently. This slide, what I show you here, is just you have to look at the dates. CT has been exploited, has been utilized all over the world by international researchers as early as the late 1990s. Fortunately, we have now machines in South Africa available where you can bring your sample, you can utilize and actually be on par with international researchers as well. A little bit of we are proud at Nexa that although we are not an institution, a higher education institution, we support higher educational institutions, and throughout the years we have postgraduate output in terms of PhDs, MECs, up to 64 over the years, being where students utilize our facility and for higher educational purposes. But also then, when you look at our outputs in terms of papers, this is my personal application here and showcase, where I have as main author up to about 27 publications, but at the end of the day, as co-authors, as well as where we are being acknowledged, up to 130 papers. And you can actually see after the 2011, when X-ray CT came into play, that we have quite of an exponential rise of publications, which we supported at Nexa. What about this geosciences field? We supported geology and also petrophysics with the output of 6 peer-reviewed papers, 1 honors, 4 MSCs, as well 3 peer-reviewed papers in the petrosciences. We can actually add another one here because our latest publication is with the University of Pretoria, James Roberts, in megakrites from Marion Island. And actually you can see the nice shape here of the olivine with endoclinopyroxene being distinguished here very nicely. And also the scale that you have here. Last announcement is our ImageRad conference in 2019, where researchers from our institution that utilizes our facilities are being asked to present their work at our facilities. So the abstract submission deadline is there, and I should have done that. I have some advertisement here of that conference, and yeah, I would like you to take one when we finish off. Okay, so the last quote: "A dream that reaches just below the stars aims too low." So for you as postgraduate students and students here, when you dream for something to get true at the end of the day, just don't dream low. You have to reach for the sky and beyond, and work hard to get there at the end of the day. So I would like to thank you very much for your attention, and also I hope that this was also for the students aspiring in order to utilize then our facilities and CT facilities in the future. I thank you very much. Thank you.
Thank you, Frikkie.
Thank you.
Is there any question? Please.
How do you integrate your neutron data with your X-ray data? You have to have a fixed point that you...
Yeah, there are one facility or two facilities in the world that does that. That has, when they have a sample, where they have a neutron beam as well as an X-ray beam simultaneously. Because if you like to match them,
my question is that at Nexa, I go from the neutron facility to the X-ray facility, and I get two loads of data.
yes, yeah.
How do I mean, given the small scale, how do you merge those two sets of data?
Okay, you have to evaluate each one of them individually, but if you say merge them, that you actually superimpose one data set onto each other, onto the other one. So it should be the same scale, and that's why it's very difficult when you doing those not simultaneously to create that kind of same voxel size, because you have to end up with the same voxel size. But you can actually, with your sample, virtually resize your sample. That is possible. But two facilities in the world, one is at NIST in America, as well as the one at FRM2 in München in Germany, has the two facilities. The neutron beam, as well as on an axis 90 degrees to the X-ray neutron beam, they have an X-ray source with then the same kind of voxel size from that sample. So it's a geometry that plays part. So simultaneously, they gather then the two sets of data and then they merge it. Then it's possible to merge it very easily. Otherwise, you have to resize, and then you can make some difficult for you at the end.
Please go ahead.
Thank you, Frikkie. That was great. Can I ask, you mentioned that signals have to be benchmarked, right? And so for X-rays, it's obviously based on attenuation and density.
Yes, yeah.
But you showed that for neutrons, it's much harder, much more scatter in that relationship. So how do you do the benchmarking for neutrons? How do you decide that this particular signal response corresponds to clinopyroxene versus plagioclase? What do you use to the benchmarking?
That is where the experts on the geosciences has to come in, because you, in your sample itself, with a thin section, you can identify which one of those, and then your voxel value that corresponds either with the X-rays or neutrons, that should be different. You can then benchmark it with that size or that part of your chem scan, or with what you visually see in that virtual slice of your X-ray or CT data set. So that is how you benchmark it. So you benchmark then the shape. That shape is, say for instance, a spherical shape. Now you have a circular sample object in your thin section, and that slice in your 3D data set will also be a circle. So you can relate then immediately with X, Y, and Z orientation. That is the particle that you are talking about. And when you know that's gold, then that particle should be gold. But eventually, when you have only gold, high densities in terms of X-rays and low densities within one sample, and you know that high density should be gold, then you know that as gold. But then you can make a mistake, because you have that other kind of material, galena, that effectively they have different densities. But in your X-ray X-ray virtual data, you can't distinguish. It's very difficult to distinguish, and therefore I mentioned that maybe your dual energy X-ray will distinguish then much more easier between those two elements.
And just a logistics question. The neutron tomography at Nexa, when does that come online? Is that online already?
No, no. Hopefully by the end of next year.
Okay. And what sample size will be accepted?
It depends on it, because when you do tomography, you don't want to create artifacts. You need to have penetration of the radiation through your sample, and in any direction through the sample. So it depends on your sample whether you have approximately 10%, more than 10% neutron or X-ray attenuation through your sample. Then you are sure you will not be able to create artifacts within your 3D data set. That is effectively the criteria. But nowadays, with the experience that the guys of my laboratory have and we have, we can actually say this sample is too heavy. You will not get penetration either with X-rays or even with neutrons through that. That's why the initiative to have also gamma rays. But also on our new facility, we will have also fast neutrons. And fast neutrons will penetrate much more deeper or better through thick materials rather than thermal neutrons. So the aspect of fast neutrons, thermal neutrons is another lecture. But nevertheless, you get those when the neutron is being born, you get fast neutrons. And then those fast neutrons can't split an atom again, the uranium atom. You need a thermal neutron, and then you use water to scatter those neutrons in terms of its energy, so that create thermal neutrons, and then the atom can be split again. So we create thermal neutrons, fast neutrons, as well as gammas from the beam. So when the atom is being split, you create gamma beam, gamma rays as well. So our new neutron radiography facility we will be able to have fast neutrons, thermal neutrons, as well as gamma rays. So with certain filter materials, bismuth and those things, we can filter out some of the spectrums, and we can have a predominantly gamma beam, predominantly fast neutron beam at the end of the day.
We have last question.
Okay.
Thanks. With the data processing side of things, do Nexa offer maybe training or help with processing data? People can go to Stellenbosch or to Gerrit, they get the data stack and then they extract their information. You guys only use particular packages.
Yeah, we have only VG Studio software, but what happens is, due to the fact that most of the researchers and the students in South Africa, CT data sets, and CT is a new kind of analytical probe. We at Nexa really support the students from the beginning until the end. So depends on the kind of research object. There's a research question that has to be asked. We support that student in the scanning of the sample, in the methodology of how X-rays and neutrons interact with the sample, to interpret then your radiographs, but also to interpret the tomograms. But again, having the last part where the sample is being analyzed, we really are being mentors to researchers and postgraduate students to support them as in order for them to generate their own data set. So it's a new software package, and that software package is not easy, it's really difficult, but we support them from the beginning. I think you will be able to tell with Kobus and Lunga supporting you in all the way to teach these researchers to generate their own data, but we are always there together. Even at the end where the publication comes into play, that we also support the review of publications as well as theses, because CT, when you describe CT and you're not familiar with terms, you can actually make a mess. So we support then and review chapters of students and researchers as well as publications in this regard. So for Nexa's side, we really walk the second mile with the researchers at the end.
That's good. Thank you.
Okay, thank you very much.
Thank you, Frikkie.
Okay, thank you.
I can't remember.
I can't remember, but there is also next week.
Tomorrow is, next week is the last Geotalk for the semester.
So,
Say about that.
thank you. Bye.
Thank you. Thank you.
Thank you. Thank you for the drinks and the...
Oops. I've got. Yeah, I've got.
Thank you.
Hi, Frikkie.
Oh, yeah.
Anthony,
Anthony.
I'm coming to you next month. How do I know what size my sample should be?
That is why, it depends then. What we normally do is we do have try to do a proof of principle scan. And in that one scan, we can say, right, this sample is too large, it's too thick. And then when you have your beam time, you really know what is your sample criteria, what is your scanning criteria. And that is where but you have now the 2 days.
I've got a week and then I've got another 2 days.
Okay, so the first day, the first day is actually try to, as a kind of a research time, where we really say, right, this sample, can you cut your samples at the end of the day, or is it not possible to cut
No,
your
I can
samples?
cut them, but I mean, if it necessitates coming back here, that's my worry.
Yeah. So the main thing is, if you, the guys do, when you lose a little bit of time, beam time, we are doing scans overnight. We put this, say, 2 or 3 samples overnight, and then we can actually gain them on what we have lost at the end of the day. But normally what we do is we prefer a test scan for the researcher really to see and to know what is the kind of sample, the thickness of the sample, the size of the sample, and also somehow the scanning parameters, because sometimes you need to scan 2 or 3 scans, but Kobus and Lunga, they already, this sample, right, let us scan it and we get an optimum scan. So they know exactly at the end of the day. But if you have a sample here,
One on me, but can I deliver one to you?
Or I can take one with me, and then, because you are...
The problem is I don't have one
Yeah, okay.
So
Yeah,
it's,
because then I could have, could have scanned it and said, "Oh, these are the results. Okay, it's too thick, maybe cut it in half or something." But do you have draw calls or what kind of samples you have?
no, it's from rock face underground. So
Okay.
it's Wits based and stuff.
Yes, yeah. But large
Well,
sample?
they are a lot, but I mean, I can obviously break them down into smaller sizes.
Yeah,
But
yeah.
the problem is I'm looking for individual grains if you run them.
Oh, and then we need a little bit more smaller samples, yeah.
Okay, so I mean, if I had a large sample, I could break it up into a couple
Yes,
of pieces.
yes,
And
yes,
then you
yes.
could do each individual
Yes,
piece.
yes, yeah. Okay.
Good.
My name is Louis Ashwell.
Louis.
My name is Louis Ashwell.
I'm so sorry.
Okay, how are you? How are you?
Excuse me. I'm related to her.
Yeah.
If you bombard a sample with neutrons, a big piece of core or something, is that going to fuck up the isotope ratios in the individual minerals inside of it?
When you have, when you have, if you need to do that kind of analytical work, you do that prior to X-ray and neutron scanning.
You can't because you dissolve the mineral in acid.
Yeah, but if you take a smaller, you take a
So
smaller
the
piece
answer
of
is yes. The neutrons will change the isotopes.
Good.
we haven't done any work on that.
I mean, even in theory.
What we did is when Francis Thackeray came to us in the 1995 that time. Oh, I can actually take this off.
And you can shut off the
When he came to us, he actually, and he has his fossil. They have done work on an elephant skull, or elephant tusk, in order to find out whether there are any changes